All right, thank you so much. Again, thank you all for being here. I'm sorry I couldn't be there in person. I want to talk a little bit about a project that I've been a GA on that is investigating the accessibility of library, archive, and museums, abbreviated to LAM, documents, physical documents primarily that have been transcribed, and making those documents accessible in digital collections. A little bit about the team. Our research team is led by PI Dr. Victoria Van Heining within the iSchool, as well as Dr. Baron Jordan, who is assisting with this research, and myself, doctoral candidate in the iSchool. So the project that I'll be talking a bit about today is Crowdsourced Data Accuracy, Accessibility, and Authority. It's a project that's been funded for 3 years and is currently in its second year and supported by the Institute of Museum and Library Services, with an aim of making crowdsourced transcriptions and crowdsourced tag data more accessible to users who have print disabilities, and understanding their experience working with assistive technology to access digital cultural heritage content. So the project has 3 major research questions. The first 2 research questions are oriented around the back-end data management side of cultural heritage data management. So I'm focusing in on the user-centered and accessibility-centered research question, which is when crowdsourced transcription data is successfully integrated into a content management system, is it accessible to people who are print disabled, in this case meaning blind or low vision, and use assistive technology? We're looking at documents kind of like the one I have shown here. Actually, this is one of our testing documents. The original document on the left with the transcription displayed on the right, and having users explore the record to parse the information as it's been transcribed, using various assistive technologies, including screen readers, magnifiers, braille keyboards, etc. To date, in early 2024, we conducted 4 accessibility user testing interviews, usability testing sessions with blind users, with 8 additional sections being conducted in May and June. Interviewees come from 4 continents, have diverse national, ethnic, linguistic, gender, and academic identities, and a wide range of familiarity with the kinds of resources we are testing. To test this, we're conducting research interviews that take between 90 and 120 minutes. We are using partner data from different library, archive, and museum institutions and having users test those platforms, the kind of data that are hosted and publicly available, and should theoretically be accessible to users. Participants search for a specific phrase that we know is in a transcription and is at least theoretically indexed in a search system and able to be discovered by inputting that text. We ask participants to read a clean transcription as well, with consistent headings and structure, and compare that experience to the live versions available on websites, on LAM websites. We have some additional resources related to our research as a Terra library and GitHub. We're also being informed throughout our research by the plain language guidelines, by Section 508 and WCAG guidelines as well. Just thanks again to my teammates, Dr. Van Heining and Dr. Jordan, to the partners and advisory board members that are supporting us, and to the IMLS for supporting the research as well. And I'll end with just some good practices that we've already come away with from the research that we've been doing with both practitioners and our print disabled accessibility testers.
Okay, thank you.
Very pleasant evening to all of you. I am Biswaksan Patnaik. I'm a PhD student from the Department of Computer Science. And today I'll be presenting our work, VisTorch, interacting with situated visualizations using handheld projectors, that I co-authored with Dr. Hui Shupeng and Dr. Nicholas Emquist. Data is everywhere, and visualizations are used across different contexts. Visualizations are not just used by data analysts in an office setting, but also used by museum tour guides to show different patterns, used by an artist to design a certain painting that guides the eyes of a user. It's also used by theater stage designers who use set plots to design theater stage. It's used by sales representatives to show feature comparisons across different products. It's also used in brainstorming as well as in education. But visualizing data can be difficult because spatial data is best analyzed in situ, but existing mixed reality technologies can be bulky, expensive, or unsuitable for collaboration. Implementing ubiquitous displays is a non-trivial technical challenge, with each solution having its own drawbacks. For example, fixed displays are static, whereas mobile displays are typically limited in size, thus limiting the area and potential for any data embedding. Augmented reality using head-mounted displays is nearly ideal for this purpose, but such devices are costly, cumbersome, and have a personal screen. Even handheld AR, which is trivial using current mobile devices, is troublesome because the imagery is shown on a personal screen, making establishing diaxes between collaborators really awkward. This gets us to the question, how do we create an ad hoc display for sense-making in a physical space that is suitable for collaboration while still being portable? We present VisTorch, a handheld device for projected situated analytics. VisTorch is a camera projector system that reads fiducial markers placed in the environment and projects a perspective correct display on the surface. Thus, placing fiducial markers on any surface enables projecting onto that surface. It provides a hand-controlled people interaction in physical space, which affords didactic gestures. This enables embedding visualizations in physical space. There are three primary components to the VisTorch hardware: a laser projector for displaying visual contents, a camera to read Aruku markers, and a trackpad to facilitate interaction. We use Aruku markers placed on flat surfaces in the environment to enable tracking the position and orientation of the device. We calculate a perspective transform to apply to the displayed imagery, which makes it possible to render a distortion-free view of any data visualization in space, even if the device is held oblique to the surface. The visualization undergoes a perspective transform such that they look pinned to the physical space, even if there is any relative motion between the hardware and the surface. Different surfaces act as placeholders for placing visualizations. Visualizations from a predefined list can be placed on any surface, and visualizations placed on any surface are tagged to those surfaces. The user interface of the VisTorch system is rendered in the browser and is built with standard web technologies such as HTML, CSS, and JavaScript. And VisTorch is compatible with any web-based visualizations. To understand how VisTorch is used in a sense-making task, we conducted a study and we observed that the spatial sense-making strategies with VisTorch are similar to other mixed reality solutions such as HMDs and large displays. And not just that, we also performed an expert review with 4 professionals drawn from varying fields with situated data to derive realistic and practical use case for VisTorch. E1 is a creative technologist and educator at the Smithsonian Museums. E2 is a projections media designer who specializes in cinematography. E3 is an environmental education coordinator who works with the School of Conservation. And E4 is an economist and information science PhD who develops statistical software. And some of the insights from the expert reviews were spatial reasoning. E1 mentioned using VisTorch in museum tours to show shapes and patterns in paintings that may be invisible to the untrained eye. E2 remarked on spatial arrangement in set installations for a crew, where VisTorch could be used to project the set plot. Engagement and efficiency. E3 noted that VisTorch affords a dynamic way of presenting data in situ that keeps students engaged. And collaboration. E4 mentioned using VisTorch for collaborative brainstorming. Thus, we see handheld projection systems show ample potential for sense-making. They're portable, they incorporate physical space ad hoc, they embed visualizations in physical space, They are collaborative and also hold didactic affordances. Thus, in summary, we have presented VisTorch, a handheld device for projected immersive analytics in physical space for ad hoc and collaborative scenarios. For more details, please refer to our work. Thank you.
Okay, so good afternoon, and thank you for sticking around. This talk will briefly cover aspects of the graphicacy skills of people with Down syndrome and describe a few of the accessibility barriers that can impact their ability to use health data. So medical professionals are increasingly prescribing technology to patients to leverage their health data during decision-making and to manage their health. The problem is that raw health data can be difficult to understand, so many health systems instead use data visualizations to better support users. This is a good idea in theory, but in practice, health data visualizations can be confusing or even scary. Unfortunately, most health data visualizations and the health systems do not have input from people with Down syndrome when they're designed. Inaccessible health technologies with poor usability can create unnecessary barriers to people with Down syndrome and limit their ability to adopt and use such systems, make informed choices about their bodies, and advocate for themselves in health contexts. So why are health data visualizations so hard to read? Well, health data visualization literacy isn't one, but 5 different literacies, each with their own underlying skills necessary to read and interact with visualization. These skills occur across 3 stages. In the first stage, the viewer identifies the component parts of the health data visualization. In the second stage, they compare and observe the relationships between these elements. And in the third, they connect that information with outside or pre-existing knowledge to make inferences and insights about potential changes to their behavior. However, this is not a linear process. Instead, it's in flux as the viewer takes in more information and their mental model updates. This qualitative studies materials and methods were co-developed with a self-advocate who has Down syndrome. And we also recruited using a variety of means. We asked several questions for each of the 6 types of health data visualizations. And the study's 10 participants had to be at least 16 years old or older, have Down syndrome, use technology, and be able to verbally communicate. We used a grounded theory to analyze nearly 700 quotes directly from participants with Down syndrome, so not from study partners, and over 11 hours of interview data. And so while we have many more findings, which I will happily talk to you about later, we're just going to kind of talk about the few accessibility issues that we identified and some other interesting things. So the first question was, the first 2 questions were related to saliency, and the act of verbalizing the graph when they first saw it showed us the kinds of personal judgments that they made about the relevance and importance of the graph's elements. It also uncovered variability in their reading patterns and scanning abilities, as some participants would fixate in areas and others would avoid them entirely. Participants read graphs using their strongest skills first, such as print literacy, and were impacted by various design choices. So looking at the mean skills across the 3 stages, we see there's kind of a gradual decline in performance in the various activities. And we posited that this was a combination of design and task-based barriers that impacted this performance. Design-based barriers can increase the number of potential errors over time because when an error goes unrecognized or uncorrected, it negatively impacts the very foundation of their mental model. And task-based barriers can increase these misunderstandings when viewers are uncertain of how to proceed or interpret the information. So for example, one design consideration is to reinforce metaphors when they occur. On the left, the vertical bar chart, participants responded by saying they're going up or down stairs or down hills. The right side is more appropriate when visualizing the distance walked. The stoplight metaphor is commonly used in US color encoding. However, 30% of our participants had no associated meaning with colors at all. And some colors, like blue, didn't have design associations, but emotional ones, as some thought that that meant sad. Additionally, the big blocks of repetitive text, such as the months and the years, are much easier to see than what's unique about each individual tick. And when you do see that tick, you have to notice the small differences, calculate the differences between them, and see the familiar numerical pattern. Versus, and like this is important for people who struggle with number sense and number lines. And that's 1/3 of typically developing Americans. So all of this should be taken with a grain of salt. Our participants were relatively young and we had a small sample size, and because it was in the US and Australia, it was more representative of the global north. However, we're gonna try to validate this in the future with a survey. And so in conclusion, this is the paper that, oh gosh, yep, end of the day. Sorry, it identifies accessibility barriers, kind of discusses the graphicy skills of people with Down syndrome for the very first time, and includes design considerations with potential strategies to improve it. And this may be beneficial to other populations who similarly struggle with the various data visualization reading skills that are necessary. So, yep.
You know you're in a data science session when consecutive talks both seem very similar while also being totally unrelated. So here we are. So my name is David Weintraub. I'm here presenting on behalf of my collaborators Rotem, Peter, and Shao. And the name of this talk is API Can Code, Situating Data Science in the Lives of High School Students. So the big picture goal of this project is, there it is, to introduce high school students to the computational foundations of data science by having them explore meaningful and authentic data that aligns with their interests using APIs. And so this is coming from a place where we're acknowledging that data science and skills associated with data science are foundational for students graduating from high school to be informed, digitally literate citizens in the world. While also recognizing that students are creating and consuming data nonstop all the time. And so we're exploring ways to create this interest-driven data science curriculum to situate data in their lived experiences and do so by harnessing data made available through publicly available APIs. So what does this look like? So we've created a high school curriculum. It has 3 units, and each of those units has a corresponding technology. The first unit we call Data in Learners' Lives, and the idea here is to introduce high school students to what data is, the role that it plays in their lives, where it comes from, who collects it, what it's used for. And for this portion of the curriculum, we're using a platform called Rapid API that's an online aggregator of publicly available APIs that share data on all sorts of topics. The second unit is we're trying to lay the computational foundations of data science, and so this is helping high school students understand the role that programming and computer science plays in data science. And so for this, we're using a platform called EduBlocks, which is a block-based implementation of Python. There's a picture of it at the bottom. And then the third unit is called is focused on data science practices. We're using a tool called CodeApp that's a really cool, clever, interactive data visualization platform. And the idea is that these 3 technologies pieced together collectively represent the data science process. And so the final project of this course is for students to pose a question about something that they're interested in, identify a data source, write a program to retrieve data on that topic, and then go through a data visualization, data analysis process to come up with some insights, a way to answer that question. So for this past year, we collaborated with a public charter high school in Washington, D.C., and had worked with a teacher who taught our curriculum. And so to give you a sense of what this looks like in action, one of the final projects of our students asked the question, is Janae Aiko a star? Who here knows who Janae Aiko is? A few of you. So there are a few people who are cooler than I am. So there's a lot of things that I love about this question. First, right, so if I'm a teacher, like I'm not going to build a curriculum around Janae Aiko because I do not know who Janae Aiko is. Second, the is Janae Aiko a star? Like, what a fabulous question in terms of needing to think about how, like, what data is going to answer this question for us, right? There's no database that says like yes or no. Instead, we need to operationalize this. So there's a lot of different ways to think about what it means to be a star and how to define a star. So there's real meaningful data science work that goes into answering this question. Okay, so the student decided to ask, is Janae Aiko a star? Found this publicly available API from a platform called Deezer that aggregates all sorts of music information in terms of songs and popularity and rankings and charts and blah, blah, blah. The student then wrote a Python program in EduBlocks that queried the Deezer API, looking for songs that had Janae Aiko as the artist, and then organized that data and turned it into a CSV, which is what we see on the right, and then took that CSV and imported into the CodeApp platform, and then produced, so in the background here we can see the tabular form of the data, and then the student came up with two visualizations. The first was, and apologies, it's a little hard to see, but it's essentially looking at artists and song names. And so Janae Aiko is the one that has the most dots, but we also see that Janae Aiko has collaborated with artists, including John Legend, Drake, Big Sean, and others. And then also looking at the years when her songs came out, and we can see the kind of the frequency of when these different songs were published. And then in the curriculum culminates with a presentation to classmates. And so this student posed this question, is Janae Aiko a star? And part of her answer during the presentation, she said, the answer I reached for my driving question was that Janae Aiko definitely makes a lot of hits in her music. During the data I've collected, I found Janae Aiko was more popular than I thought she was. So here we see a student choosing a topic that she cared about, identifying real data out in the world, writing a program to retrieve it, doing some level of data analysis to make sense of it, and then coming up with the conclusion. I suspect that she knew Janae Aiko was a star before she started because she loves Janae Aiko. But nevertheless, we can see this kind of authentic data science process happening in a high school classroom in a way that's situated within the lives of a high school student and who the high school student was and what the high school student cared about. If you'd like to learn more about the curriculum or see other examples of our work, please come visit our poster outside. Thank you.
Thank you, David.
Okay, so my name is Pramod Chunduri. I'm a PhD student affiliated with the HCIL, and I'm from the high school. So I'll be presenting results from a design study that we conducted for making charts accessible for blind individuals on touchscreen devices. So this work was done in collaboration with Yasmin Riazuddin, Dr. Bun Jordan, Dr. Jonathan Lazar, and Dr. Nicholas Enquist. So the data visualization research community continues to make tremendous progress to help individuals make important data-driven decisions. But visualizations are largely inaccessible for about 285 million people with low vision and about 39 million individuals worldwide. And we've seen quite a few talks on issues with visualization and the need for accessibility. Sensory substitution is this idea, it's a common technique in the accessibility world used to help individuals overcome vision challenges and provide better access to information. It's this idea of transforming visual stimuli into other sensory modalities such as touch, hearing, and even smell. If you want to know more about smell and data viz, there's a smell guy right there. His name is Biswaksin. Talk to him. So what do we do in our study? In our study, we explore how to effectively employ sensory substitution to support visualization-related tasks. So more specifically, we talk about cross-modal sensory substitution in this paper. It's this idea of replacing in real time the output of one sensory system with the output of another sensory system. For example, in our solution, we're trying to replace the sensation of touch with that of audio. Although you do feel touch, the meaning or the data is encoded to the sound and not the haptic feedback that you get. Right, so what did we do? So we first conducted 3 design sessions with our collaborator. We had some initial ideas in mind on how to design the audio. So there's a little bit of interaction design, sound design, and all of these things, different modalities that we had to think about. So once we had an initial set of ideas, we conducted 3 design sessions with our collaborator. She's blind and she's very familiar with scatter plots and had to interact with a lot of visualizations during her graduate school work. So we used tactile graphics printed on thermoform paper as a design material in the workshop, just to understand and contrast with this whole notion of maybe cross-modal sensory substitution and how we can maybe train people or like build up the technique. So we specifically chose scatter plots for our study, and after 3 design sessions, we made some improvements, and when we tested it out externally with some external reviewers. So Our reviewer was actually deaf-blind. We were not looking for someone who was deaf-blind, but we had to run the study, and we wanted feedback on graphical perception using sound. And our second expert who gave us feedback was a braille proof reader, so the choice was always tactile for this person. So, and after that, we made more improvements. I'm going to show you a brief demo. I will be talking and talking, not talking at the same time.
What you're seeing right now is the interface of our TactualPlot system. We have visualized a scatter plot that has 50 points, has a medium scatter and a negative trend. Users can touch the display and drag their fingers around to trigger the non-speech sounds, and tapping gestures will verbalize the data density or tick mark value under the finger. The position of each finger touching the screen is tracked by a circle. When more than one finger is touching the display, multiple circles are shown, and the iPad supports up to 10 fingers concurrently interacting with the screen. So now let's see how the sound works. The point density under the finger, or in other words, the number of data points that are touched, is mapped to the notes of a C major scale. For example, now let's look at how one can start in the origin and move laterally from left to right to sample the sounds.
Origin, 0, 0.
Okay, running a little short on time, but the whole point is that you sample the density under your fingers. There are two modes. You tap, you hear speech. You pan, you hear notes, tones. And the audio is going to play for a few seconds and then turn off, just so that you don't overload people's ears, which is genuine feedback that I got as part of the second expert review session. So no, I'm not planning to use 10 fingers to sample sound. So what else did we do? We visualized touch positions from the workshop, and we just wanted to find out how people are exploring and what data sources we might be able to collect to further understand this technique. So in both the images on the slide, the frame on the left shows a snapshot of the initial point in the exploration, and the frame on the right shows a touch trail at the end of the exploration. As you can see, our collaborator started exploration at the origin and either moved laterally or vertically. So what else did we do? We compared TactualPlot with that of tactile graphics and found that our collaborator was able to estimate values at a comparable accuracy as that of tactile graphics. We were not looking to compete. We were just trying to understand if this technique is feasible. Although one interesting thing we noticed was that with TactualPlot, our collaborator preferred to use tabs, and indicated by the red circles. And then for tactile graphics, more panning, and that's what we found. So we are currently expanding TactualPlot to more chart types because we want to build up a technique that can handle many chart types, because there are plenty and far and beyond. And then this also includes an improvement to the sound design, specifically with spatial audio, so that because we're trying to encode some spatial perception, which is why it's a form of interactive sonification when you think about it, because it's laid out and then sound is actually going to be triggered at a particular place in a particular form. So that's mainly the idea. Thank you for listening. And if you have questions, please come find me later, or you can ask me later. Thank you.
Thank you. Hi everybody, my name is Jimmy Lin. Today I'm presenting you on switch mode, how one environment supports multiple strategies to transition from block-based programming to text-based programming. And this work is part of my dissertation in collaboration with David and Jason over there. So we're gonna first start the question is, why do we use block-based programming? So for those of you who didn't know, block-based programming is this like picture you can show on the left side. You have a bunch of blocks you can drag over to the middle section and stack it all together, and then make the cat move or make a meow sound. And it's been proved that it's very easy to get started. It's syntax-free, it's very colorful, and can do animation, storytelling, and physical computing. However, we do have a problem here. So with the block-based programming on the left side, you can see the text-based programming on the right side. I would hope nobody thinks these two look similar, right? It's very different, and how the students go from the left side to the right side. And also, why do we need the transition? Because the AP Computer Science A course is a text-based programming course with Java. And if students want to go on a CS career, like going to Facebook, Google, and any other big high-tech companies, they need text-based programming. And from previous research, that students feel authenticity with the text-based programming. And when it's a sudden transition, students feel they are learning a brand new language. So my first research question is, how can we design a hybrid programming environment to support text-based programming inside the block-based programming? And the answer of it is switch mode. And the second research question looks at what programming strategy the learner develop when using switch mode. So these are the bunch of related works with use blocks only, single view dual modality, bidirectional dual modality, one-way transition, and hybrid. In my work, we focus on the hybrid sections. So we designed switch mode with two major features. The first one is a convert. You right-click on a block, and then you can hit convert it to switch mode, and you can see it's converted into the Python. We also support the C shape, which we know that you can do the for loop or conditional statement here, and then the inside will keep in the blocks. And we also include the typing feature as the autocomplete and syntax highlight as a professional IDE that is needed. You can see here that the drop-down shows whatever the prompt that autocomplete prompts you. And when you finish typing in a correct syntax, the text changes into a different color. And these are the scaffolds we designed for students to go from block to text. And we include the environment inside in collaboration with VAX Robotics, and this is built into the VAX VR, which you have a virtual robots in there to move around, to knock over the castles, or go through a maze. So I did a study in a classroom-based study in a high school in a Midwestern city in a total of 8 students. And we give them an interview coding activity saying, go to a randomly assigned number, and they're required to use switch mode to go back from the number. When they go over there, they can use block, switch, or Python, up to their choice. But on the way back, they need to use switch. So we want to examine how they actually use switch mode and the hints along the way. So the findings from the coding activity is in total of 8 different strategies, going from the most scaffolded on the top, which is convert only. Basically, you do everything in blocks and you right-click and get it converted. That's the most scaffolded because you're not tinkering anything in text-based. And the least scaffolded is going to the bottom, which is type without autocomplete. We'll go into the details. I'm gonna only show a couple here, but if you want to know more, come to my poster. This particular one is convert and modify parameters. So the learners compose with conventional blocks, convert into switch mode, like the top one, and then exclusively modify the parameters in switch mode. So modifying switch mode, you can see it changing from 90 degrees to 180 degrees. If I'm a student, I want to just change the degree of it turns, it's quite easy to know where I should change in that Python commands. Next one is type convert then reference. So the students might start dragging a switch mode block into the canvas, start typing, and when they type halfway, you can see on the second line, they haven't made a mistake, the text didn't change. And then they didn't know what to do, and they say drag over a regular block, drive forward, and then right-click, convert it, and then use the converted blocks as a reference to complete their half-baked commands. The last one is the type without a complete, so the learners drag the switch mode over and then manually type in the command and deliberately not using the autocomplete feature. They will still see all the prompt in the bottom, but they type every character by character. So here's the 2 data visualizations I did with all these 8 students. If you want to know more, come to my poster. I'm going to conclude with the student conclusion is that students use switch mode with all their scaffolds, and they step out of their comfort zone, whether it's blocks only or certain text-based commands, into the zone of proximal development. It's switch mode or more text-based commands, and eventually hoping them they can go into the text-based programming. I'll conclude with 2 quotes from 2 different students. First is saying, I wish we could use it to more people because students know that they are in a beta environment. And second, students saying, there's a lot of stuff like it opens my window and it gives me more leeway. Like I can choose because in the future, there's going to be a whole bunch of jobs that need this type of computer science. In hoping that we see that students go into computer science career if they desire to choose so. And with that, thank you.
Thank you, Jimmy.